A graph of a function is nothing more than just a plotting of points that make the equation true. So graphs of functions, as we've seen before, must pass the vertical line test because we learned that a function implies that every x that you plug in is only going to give you one output for y. Now we've learned quite a few parent functions or basic functions, but we're just going to take a look in this slideshow with three of the most common ones. In addition to the three that we see, we're going to be talking about exponential functions and logarithmic functions and identity functions or square root functions. They all have their own shapes for various reasons, but the processes that we take in order to move them around our graph is going to be the same as what we see today. So let's take a look at our first equation, f of x equals x squared, which is referred to as a quadratic function. And we see that this here is a representation that we refer to as an equation because it's telling us that f of x or y is equal to whatever the input is squared or times itself. So if we look at another representation as a table, then we could choose a few different inputs. Let's say we choose 0 in order to find out what's going on right at the y-axis, and then choose a couple points on the right side, say 1 and 2, and a couple of x values on the left side, -2 and -1. Now notice that when you square 0 or multiply by itself, you get 0. But also when you square 1 or -1, you get the same answer because a positive times a positive is positive, and a negative squared is also positive. And if we now square -2 and +2, we end up getting values of 4. So this is why when you graphed your parent function, the shape of this quadratic function looked like this curve that we refer to as a parabola. Now this parabola has a domain of -infinity to infinity, because that means that from the left to the right side of the x-axis, we can plug in anything we choose to, and when I square it, I'll get a y value. As for the range, we should realize that the lowest this graph ever goes is a y value of 0. It never goes down into the negative y values. So the range is going to be 0 to infinity, including 0. Let's take a look at our next parent function. How about the cubic function? This now tells us to take an input and multiply by itself 3 times. So notice the slight difference between this function and the quadratic function. If I cube 0, I still get 0. And if I cube 1 or -1, I still get values of 1, except that now when I multiply a negative number by itself 3 times, I get a value of -1. And if we now cube each of these values, -2 and 2, we get values of 8 or -8. So look at how this changes things. This means that if I choose the input of -2, my y-coordinate is downwards 8 units. An x-coordinate of -1 gives me a value downwards 1 unit, which is why this graph does not look like a parabola, because negative inputs give me negative outputs. So you can see the domain is still going to be -infinity to infinity, because anything I choose for x and cube is still going to give me an output. And my range is now going to be -infinity to infinity, because this graph goes downwards forever and it goes upwards forever. Let's take a look at the last type of parent function for this activity, and that's going to be the absolute value of x function. If I take an absolute value of a number, that just means the distance that that quantity is from 0. Well, 0 has an absolute value of 0. 1 is 1 unit away from 0, and -1 is also 1 unit away from 0. And finally, 2 and -2 are both 2 units away from 0. So what a lot of people recognize is that when you take the absolute value of some quantity, the output becomes a positive answer. So if I were to now plot these points, notice this resembles a quadratic function in a way, because positive inputs give me positive outputs and negative inputs give me positive outputs. But now you can see that it's a line on each side forming a V. And the domain and range for an absolute value function is going to be exactly the same as the corresponding quadratic. So now let's take a look at the function f of x equals x squared and look at this in a little more detail. Okay, remember that this is going to give us a quadratic function that forms a parabola. And notice that these are the same values in the table, so in order to plot these, we plot the x-coordinate of -2 and the y-coordinate of 4. Plotting the x-coordinate of -2 and the y-coordinate of 4. And the same thing goes for each of the rest of these values, which is why we form the parabola. But now I'd like to take a look at this next function. What if we take a look at the function x minus 1 quantity squared? Notice that this is a bit different than just x squared because it's saying before you square this quantity, subtract 1 from the x value. So why don't we take a look at -2? If we were to plug -2 into that function, this would tell me to take -2 and subtract 1, which is -3. And when I now square -3, my output becomes 9. I'll ask that you pause this video and just verify by plugging in these other x values that you sure enough get these outputs. Now, if we were to plot these outputs, notice that this would tell me to plot an input of -2 and a corresponding output of 9. This would mean plug in an input of 0 and an output of 1, or an input of 2 and an output of 1. These are all ordered pairs, and if I plot them, notice this is our graph. And what we should recognize about this is that that blue graph looks identical to the red graph, except that it seems to have been shifted to the right 1 unit. In fact, every single point was shifted to the right 1 unit. And therefore, if we ever see some quantity being subtracted or added to x, that's going to also move my graph to the right 1 unit. Okay. So if we take a look now at another function, what if we were to now look at x squared plus 3? Notice how that's a little different. I don't see any parentheses. I don't see any quantity where I'm adding before I'm squaring. This one is telling me to take an input and square it, which is exactly what the red function told me to do, and then add 3 more. Well, notice all that's going to do is it's going to take all of the outputs that I already got for the red function. It's going to take all the x squared values, and now I'm going to add 3. So if I add 3 to 4, I get 7. Add 3 to 1, I get 4. Add 3 to 0, I get 3. Add 1 to 4, or add 3 to 1, and I get 4. Add 3 to 4, and I get 7. So notice that now I have another collection of points. This tells me the point is -2, 7, -1, 4, 0, 3. And if I were to now plot each of those, notice that this is the new graph. It appears that that graph has moved the red graph up 3 more units. It looks like the same shape, but it's moved. In fact, it hasn't only moved that first point up 3 units, but it's moved every single value or every single point on the red graph up 3 units. Which is why if you ever see a number added or subtracted to the end of a function, that's going to cause you to move the graph up or down. So for this next set of examples, let's take a look at the next parent function of x cubed. Remember the inputs and outputs for this function. That's why the graph looks like this snake curving through the origin. Well, let's take a look now at this function of -x cubed. The only difference between these is that x cubed is going to give us a certain output, the negative of x cubed should give me the exact opposite outputs. So when I plug in -2, I get -8 for x cubed, but I'm going to get +8 for negative x cubed. In other words, all of the outputs for the red x cubed function are going to become the opposites. And so if I now plot each of those points, I should figure out that I get the blue graph. And what you should notice is that all of the positive outputs in the top right become negative outputs in the bottom right. All of the original negative outputs in the bottom left become positive outputs in the top left. And therefore, we refer to this as a reflection over the x-axis. So now let's put all of these transformations together into one function and see how that affects the graph. So here's our function, the negative of x plus 1 cubed minus 2. Now I'm going to encourage you to again pause the video and plug in each of these black inputs of x into this function up here, into the green function h of x, and determine what the output should be. I'll start with putting in 2. If I plug in 2, 2 plus 1 gives me 3. 3 to the power of 3 is 27. It now says make that quantity negative, so I get negative 27. And negative 27 minus 2 gives me negative 29. I encourage you to verify with the order of operations that plugging in the other inputs give you the correct corresponding outputs. Once you've checked all of those, when we plot these points, you will end up getting this function right here. And that looks like the red function, except a few things have happened. Notice that first of all, it appears to be more closely related to the blue function because of its shape. The blue function is already a reflection, which is where the negative came in. And it also appears that the red curve that passed through the origin has now moved to the left one, and it's moved down 2. So that center point of my graph has moved left 1 and down 2. And notice how we can see that, because this causes me to move left 1, while the minus 2 causes me to move down 2. So from now on, when we graph transformations of functions, if we were to find this graph right here, we would never again need to graph or plot a table of values. In fact, we don't ever want to plot a table of values because we would prefer instead to just list out what the transformations are. And after plotting the red parent function, we can apply each of those new transformations to create the new graph. Therefore, this function is a reflection over the x-axis. It's shifted left 1, and it's shifted down 2. So let's sum this up with how to recognize each of these transformations. Because every operation that applies on some function causes some sort of change or movement on the graph. So more specifically, let's assume that k in my formulas here is going to be some positive constant. Then that would imply that if we have these graphs, then a reflection on the x-axis will be demonstrated by multiplying the function by a negative. Once you do that, that just causes the entire red original graph to become the negative of those outputs. So any value that happens to be above the x-axis will reflect to below the x-axis, and vice versa. Taking a look at a vertical translation, notice that those are going to occur when you add a number to the end of the function. So adding a number to the end of a function will change the output by adding that amount or moving the graph upwards. If I now subtract a number from a function, then that will cause the graph to move downwards that far, or k units in this case. But that should make sense because adding a number causes the output to be larger. Subtracting a number causes the output to be smaller, and therefore that moves down k units. Lastly, horizontal translations or horizontal transformations occur whenever you're adding or subtracting a number directly to x. So whether that's inside of an x squared function or an x cubed function or an absolute value function, if I'm ever adding or subtracting a number directly from x, that will cause the graph to move left or right. But the important thing to recognize about horizontal translations is that even though we're adding k, you would expect that that would move right into the positive direction when in fact it does the opposite. And the reason for that is because what do we have to plug in for x in order to give the input of 0? And it would always be the opposite of the value k. What if we see a quantity where we're subtracting k from the input? If we ever subtract k, that causes the graph to shift the opposite direction, or in other words, moves to the right. So if we recognize that the vertical translations move in a direction that corresponds to the sign, horizontal translations move in a direction that is opposite of the direction you expect. So as we saw with the previous example on the previous slide, we can put all of these transformations together into one function and list out the types of transformations so that we no longer ever have to create a table in order to plot our points to graph. Instead, we plot the red parent function, which is the basic shape, and then we move the graph accordingly.